You know, our sun, it's the engine of our entire solar system. For centuries, we've done our best to watch it, sketch it, and measure it. But today, something's different. We're not just watching anymore. We're actually teaching machines to read our star in ways we never, ever thought possible. So let's dive in and see how this incredible intersection of artificial intelligence and solar physics is changing everything.
Okay, so our story really starts with data. A lot of data. Believe it or not, scientists have been systematically observing and recording the sun's activity for over 400 years. That's a pretty unique and incredibly rich scientific measurement streak, and it's given us this immense historical library of our star's behavior. But you know, that historical data? That's just the tip of the iceberg. Today, we're in a total data deluge. To give you an idea, just one spacecraft, the Solar Dynamics Observatory, sends us a new super high-resolution image of the sun every 12 seconds, every single day. I mean, we're talking about an absolute flood of information.
And that right there is the central challenge, isn't it? With terabytes of data streaming in constantly, how can any team of scientists possibly keep up? How do you spot those crucial, fleeting events, or those really subtle long-term patterns? Seriously, how do you find that one needle of discovery in this cosmic haystack?
Well, the answer, as it turns out, isn't a bigger telescope, it's a smarter one. The answer is something called machine learning, and it's this revolutionary approach that's finally allowing scientists to make sense of this solar data storm.
Okay, so at the very heart of this revolution is this idea, a neural network. The easiest way to think about it is as a computer model that's kind of inspired by our own brains. It's not about programming a bunch of rigid rules. Instead, it just learns. It finds patterns in massive amounts of data, a lot like how we learn from experience. So how does that even work? Well, imagine this. Data, like all the pixels in an image of the sun, goes in one end. It then filters through all these interconnected layers of what they call neurons, and each one performs a tiny, simple calculation. And then bam, out the other end comes a coherent output, maybe a prediction or a classification or even a whole new image. So that whole learning part, it's basically a cycle that repeats over and over. First, you show it thousands and thousands of examples that you've already labeled. Then you set up what's called a loss function, which is really just a fancy term for a score that tells the model how wrong it is. The network then just tweaks all its internal connections to try and get a better score. And it does this again and again and again, literally millions of times, until it gets really, really good. All right, so with that basic idea in mind, let's jump into the first major application, which is pretty cool. Training an AI to act like a tireless, perfectly consistent expert that can watch the sun and see its secrets 24/7. Okay, so take a look at these dark patches. They're called coronal holes, and they're super important because they're the source of high-speed solar wind that can mess with our satellites and power grids here on Earth. But finding their exact boundaries, it's a genuinely tricky task. For years, it required human experts to carefully, manually draw these outlines. It's slow, it's subjective. I mean, two different experts might draw the line in slightly different places. But here's where it gets amazing. We can now train a special kind of neural network called a UNet on thousands of those images hand-labeled by the experts. And the result? Well, you're looking at it. The AI learns to do the job automatically, instantly, and with perfect consistency every single time, creating these incredibly reliable maps for scientists to work with. So, identifying features is one thing. That's already pretty impressive. But what's even more mind-blowing is AI's ability to act as a kind of universal translator, to take one kind of solar data and turn it into a completely different kind.
All right, get ready for a little magic trick. Do you think you could teach a machine to look at an image of the sun in ultraviolet light, and from that alone create a detailed map of the sun's invisible magnetic field, something we call a magnetogram? Now that sounds totally impossible, right? But the thing is, the underlying physics actually connects them. The real question was, could an AI figure out that connection on its own?
And here's the big reveal. On the left, you've got the UV image that went in, and on the right, that's the magnetogram the AI generated. It learned the incredibly complex relationship between them all by itself. This is a game changer. It means we can do things like generate magnetic maps for times when our main instrument was down. Or even, get this, use images from a different spacecraft to create magnetic maps of the far side of the sun, the side we literally can't see from Earth. And you know what? This translation superpower isn't just for shiny new satellite images.
The same basic technology can be pointed at centuries of historical data. On the left, that's a page from an old handwritten logbook. And on the right, the AI has read all that varied handwriting and turned it into a perfect, clean digital table, unlocking this treasure trove of historical knowledge for modern computers to analyze. Okay, so all this leads us to what might be one of the most critical applications of all, space weather forecasting. Because when the sun throws a tantrum, a giant solar flare or a coronal mass ejection, the effects can be felt right here on Earth, and they can threaten our satellites, our power grids, and even our astronauts in orbit. The thing is, predicting these events is, well, it's incredibly hard. The biggest problem is what's called highly unbalanced data. Basically, the most powerful X-class flares are really rare. For every one spot on the sun that produces a huge flare, you might have 800 that do absolutely nothing. So it's way too easy for a model to just learn to predict no flare all the time. It'll be 99% accurate, sure, but it'll also be completely useless. And that's exactly why scientists can't just look at simple accuracy. They have to use smarter metrics, like precision and recall. Think of it this way. Precision is like asking, when the model cries wolf, is there actually a wolf? You want that number to be high. But recall asks, of all the wolves that actually showed up, how many did the model manage to spot? You want that to be high too. It's this constant, delicate balancing act between not raising false alarms and not missing the real thing. And believe me, this challenge gets even bigger when you're talking about long-term forecasts. Just look at this. These are the wildly different predictions that various models made for the peak of our current solar cycle, cycle 25. I mean, that huge range of possibilities, from a really weak cycle to a very strong one, just goes to show how much we're still figuring out. So all of this, it brings us to a new frontier. Because these AI tools, they aren't just solving old problems a little bit faster, they're fundamentally changing the way solar physics is done. We are talking about an entirely new age of discovery. And one of the most exciting things happening right now is something called a physics-informed neural network, or PIN for short. In this case, the AI isn't just learning from looking at data. It's also being explicitly taught the fundamental laws of physics, the actual differential equations that say how magnetic fields and plasmas are supposed to behave. This gives the model a powerful reality check, making sure its answers are physically possible. So what does this actually let us do? I mean, what's the payoff? By combining what we can see on the sun's surface with the laws of physics, a pen can actually reconstruct the complex, invisible, three-dimensional structure of the sun's magnetic field as it stretches out into space. It's like giving scientists X-ray vision to finally see the hidden architecture of the sun's atmosphere. And that brings us to this really powerful idea from the research. AI is doing more than just spitting out answers. It's changing the very questions we're able to ask. As the paper says, large-scale problems can now be posed whose mathematical formulation was unclear yesterday. We're literally stepping into a new era of how science gets done. And so, I want to leave you with one final thought. This amazing partnership between our human intuition and the raw power of machine intelligence is letting us decode the incredibly complex language of our own star. So the real question is this. By teaching machines to understand the sun, are we also in the process learning a brand new language, a language to speak with the rest of the universe?